Hello, my name is Saransh and I am from India. I'm a senior research software developer in the food computing group at Ashoka University, and I'm currently working on building a semantic knowledge graph for Indian food. I completed my interdisciplinary masters in computer science and psychology in 2023, also from Ashoka University. With NMA, I participated as a student in the computational neuroscience course in 2023 and served as a TA for the deep learning course in 2024. In this video, I'll cover few parts of the week 1 day 2 tutorial of the deep learning course, which is on gradient descent and autograd. In particular, I'll be going over the autograd feature of PyTorch and give a brief walkthrough of the coding exercise 2.1. Let me scroll down to the relevant section. All right. So we know that the gradient descent algorithm provides us with one of the fastest ways to minimize a loss function or any function for that matter. All that we need to have is a suitable initial value, a chosen learning rate, and the negative gradient of the function for each time step. In the case of complex functions, calculating gradient by hand can become quite tedious despite using the chain rule. And as it so happens in neural networks, the loss functions are usually very complex. Fortunately for us, the mechanical way of calculating gradient can be automated by building something that we refer to as a computational graph. Consider the relatively complex function f of x comma y comma z on the screen. As you can see, each pink colored oval in the graph has details about a small chunk of the more complex function f. Now we start performing multiple iterations of forward pass and backward pass through this dynamic graph and end up with the corresponding partial derivatives for each chunk of the function, which can be seen in the blue squared boxes below. These values can be then combined using chain rule to get the partial derivatives of the loss function over a variable of interest. Of course, this can be done with all the variables of interest to get the gradient of a function. This automatic way of calculating the derivative of a function is called automatic differentiation, and autograd is nothing but essentially the name of the automatic differentiation engine that is used in the PyTorch library. Now let me move to the coding exercise 2.1, in which we will build a computational graph to implement a single neuron with scalar input and output. Right. So in this chunk of code, what is essentially happening is that we pass singleton matrices with the values 1 and 7 to two tensor objects which are stored in feature and target variables. In PyTorch, a tensor is simply a data structure that is designed to run efficiently on machine learning specific hardware, and it can hold the input, output, and parameters of the model. Now let me uncomment the code. Okay. So simple graph here is basically a class to which we pass the floating numbers minus 0.5 and 0.5. Let's see what's really happening over there. As we can see through the init function, we are initiating the weight and the bias variables using the tensor object and the values that we had passed earlier. Note also that we are passing a requires underscore grad keyword argument here with the value set to true. This simply means that the weight and the bias parameters are the only learnable parameters that we are interested in, and PyTorch will track every operation using this tensor while configuring the computational graph for these two parameters only. Next, we call the prediction function for this particular object of simple graph. Let me comment this out and write the prediction function quickly. Okay. I'm using TANH here because TANH is an activation function commonly used in neural networks. So essentially, I'm simply multiplying x by the weight and adding the bias. Then we calculate the square loss function by passing target and the prediction values. So I fill this by saying, all right, y underscore true minus y underscore prediction raised to the power 2. And then let me comment this out. All right. So with that worked out, Let me run this part of the code. And as you can see, the prediction comes out to be 0.0 and the L2 loss is 49.0. Thank you.